Good morning, everyone. My name is He Mingzhen. Today I will present the study we have done in Shanghai Jiao Tong University, FAGR, an efficient file-aware graph recovery scheme for erasure-coded cloud storage systems. Nowadays, flash memory is widely used in cloud storage systems. However, hardware failure and data loss are common in flash storage, especially in MLC and TLC flash, so high reliability is necessary. Replication is a traditional method to provide high reliability, but its storage cost is high. To ensure high availability and reliability of cloud storage systems, erasure coding is a typical method with low monetary cost. In the last 2 decades, several popular erasure codes are proposed. For example, RSKR can tolerate up to R failures, and data can be recovered from arbitrary K blocks. So R32 erasure-coded system can provide better reliability than replication with lower storage cost. However, due to high failure risks of disk drives, a challenge issue is how to shorten the recovery process. In the past 10 years, a few recovery methods are proposed to accelerate the recovery. Some methods speed up the reconstruction via pipelining in the device level, like partial parallel repair pipelining, and fast predictive repair. Meanwhile, several methods are given to reconstruct the hot data in advance, which investigate the data access patterns from upper-level applications. One of the state-of-the-art recovery methods is PPR. It splits the recovery process into independent tasks to enhance parallelism. The key idea of repair pipelining is to split the recovery process but in a fine-grained manner and pipeline the subtasks. For faster predictive repair, it models a bipartite matching problem for scheduling migration and reconstruction in parallel. This table is a summary on various fast recovery methods. From this table, we know that for faster recovery methods in the application level, they can speed up the hot data recovery, but achieve low performance, because the recovery process is out of order, based on the hot data distribution. Therefore, the pipelining methods in the device level cannot be applied. On the other hand, device-level recovery approaches result in high recovery time on hot files, because the file mapping and data access patterns are not recorded. Overall, existing methods cannot investigate the relationships among blocks, files, stripes, nodes, access frequencies, which reflects to a tremendous and complex graph. It motivates us to propose a novel method called FAGR to enhance the recovery performance in this paper. Now I'm going to introduce our file-aware graph recovery scheme. A recovery process of FAGR can be divided into 3 steps. First, the metadata information of files and blocks are collected, which is provided by the storage system. Second, a corresponding mathematical graph model is established based on the metadata information, and possible recovery paths can be evaluated based on the analysis on the graph model. Third, the lost data is reconstructed according to the recovery path and optimized from the file point of view. Next, I introduce terms in FAGR. Round is a basic time unit of the recovery process, in which files can be recovered partially or entirely. An online node is one of all surviving nodes. A hot spare node is a node to store the recovered blocks. Then let's turn to the construction of FAGR graph. There are 6 types of vertices: files, stripes, blocks, nodes, and 2 special vertices, source and destination. Typically, a file in an RSKR-coded system is divided into several stripes, and each stripe consists of K plus R blocks. To reflect relationships among different vertices, we use edges to delegate the mappings and distributions among these vertices. There are 2 properties of edges. The capacity is used to measure the maximum amount of data transmission required for a recovery task or subtask. The access frequencies reflect the hotness and the recovery priority of a file. To improve file level recovery performance, we have two goals. First, files with higher access frequencies are given higher priorities. Second, recovery tasks are evenly allocated to hot spare nodes and online nodes to avoid congestion. For simplicity, here we define a flow as a subgraph. Please refer to our paper for formal definitions of flow and maximum cost flow problem. The value of each edge is less than or equal to the capacity. In this way, a flow can represent a recovery scheme due to the properties of FAGR graph. The cost of each edge is the weighted sum of value times frequency. Let's take an example here. The values of SOF0 and SOF1 are both 2. The values of other red edges are 1. The frequencies of SOF0 and SOF1 are 3 and 2. The frequencies of other edges are 0. So the total cost is 10. The cost of a flow reveals the cost efficiency by taking both the hotness of files and the amount of data transmission into consideration. Therefore, we can find a recovery scheme that achieves the two goals by finding the maximum cost flow in the FAGR graph. In the example figure, we can see that the maximum flow is marked with red, and the total cost is 10. Finally, after constructing the recovery scheme, FAGR can use any recovery methods like PBR and RP to manage the data transmission and support the easy computations, and the recovery process will be finished round by round. Let's illustrate the process of FAGR with a case study. The parameters of the case are listed on the left. In each round, FAGR find the maximum cost flow and finish the corresponding tasks. For example, in the first round, S0 is recovered through N0 and N1, and S2 is recovered through N2 and N3 because of their highest frequencies. Furthermore, FAGR avoids certain nodes such as N1 participating in the recovery process of more than 2 stripes concurrently. Round 2 and round 3 are similar to round 1. To demonstrate the effectiveness of FAGR, we set up a cluster of 30 Docker containers. Use 4 traces to obtain the basic information of files and implement FAGR with Erasure library for simplicity. The evaluation platform and trace information are shown in the table. We use several metrics and methods to evaluate our scheme. In static workload evaluation, we use recovery time on different file proportions as metrics, while in dynamic workload evaluation, we use response time and throughput as metrics. And the recovery methods for comparison are typical recovery method PBR and RP. Compared with typical recovery method RP and PBR, when changing the number of hot spare nodes, FAGR can reduce the top 40% files recovery time by up to 58.06%, 57.37%, and 59.04% respectively. When alter the RS code parameter, the maximum reductions of recovery time are shown in the table. Besides, FAGR can reduce the average response time by 81.62%, 51.11%, and 68.16%. Improve the throughput by 4.44 times, 1.31 times, and 2.14 times when changing the RS code parameters, and the number of hot spare nodes in dynamic workload evaluation. In conclusion, FAGR can integrate the state-of-the-art fast recovery methods to improve file-level recovery performance in different recovery environments, and the evaluation results demonstrate its superiority over existing approaches. Thank you very much for your time. I would be more than happy to answer any questions that you might have.